A joint research team from Canada and South Korea has developed an innovative, high-performance material that's set to revolutionize lightweight engineering. Imagine a substance as strong as carbon steel, yet as lightweight as styrofoam. Yes, you heard that right. This groundbreaking material combines the best of both worlds: unparalleled strength and minimal weight, which could drastically reduce fuel consumption in vehicles, particularly airplanes. To put this into perspective, every kilogram saved on an aircraft could reduce fuel consumption by up to 80 liters per year. Modern passenger aircraft can weigh hundreds of tons, so shaving off even a fraction of that weight with lighter components can result in substantial savings and significantly reduced carbon emissions. But what exactly is this new material? How does it compare to traditional alternatives? And just how far can its potential reach? Let's unpack all of that. Reducing weight in engineering isn't just about performance. It's about efficiency and sustainability. When a car is made 100 kilograms lighter, it typically consumes about 0.5 liters less fuel per 100 kilometers. At first glance, that might seem insignificant. But across Germany, where all vehicles combined clock more than 582 billion kilometers annually, those seemingly small savings add up. If every car were 100 kilograms lighter, it would translate to a national fuel saving of over 2.9 billion liters each year. In aviation, the stakes are even higher. An Airbus A320, for example, could save nearly 10,000 liters of fuel annually for every 100 kilograms reduced. This is why lightweight construction is not just a design trend, but a critical goal in modern engineering. Enter the new ultralight material developed through the collaboration between Canadian and South Korean scientists. At its core, the material belongs to a class known as nanoarchitectured materials. These substances are structured using powerful geometric forms, like triangles, which are known for their strength in bridge construction, but applied at the nanoscale. The guiding principle here is simple but powerful. The smaller the structure, the stronger it becomes. This concept isn't new. Scientists have understood for over 60 years that shrinking the size of metal structures increases their strength. Nanoarchitectured materials exploit this concept to the fullest. They offer exceptional strength to weight and stiffness to weight ratios, achieving feats that bulk materials simply can't. The Canadian and South Korean researchers set out to combine two key properties, extremely low material density and high structural strength, into a single material. Their base component was a polymer, which is essentially a compound made of repeating molecular units. But the magic lies in how they transformed this simple polymer into something extraordinary. They used a two-pronged approach, combining the finite element method, FEM, and Bayesian optimization. The FEM is a computational technique used to simulate how materials react under various physical influences like pressure, heat, and vibration. It breaks down complex models into smaller elements, making calculations more manageable. These individual elements are then analyzed and reassembled into a comprehensive simulation of the material. Using FEM, engineers can simulate the behavior of materials under real-world conditions. For example, how a part will react during transport, assembly, or even under extreme stress. This allows for not only optimizing the performance, but also reducing development time and costs. However, FEM typically focuses on the macro scale. To fine-tune the design further, the researchers integrated Bayesian optimization, a probabilistic method that intelligently searches for the best parameters to improve a model. Bayesian optimization works by predicting the performance of unknown data points based on existing ones, using what's called a Gaussian process. This helps identify which configurations are likely to yield better results. A key feature of this approach is the acquisition function, which evaluates where the model should look next, essentially guiding the optimization process by selecting the most promising data points in a vast parameter space. Think of it like mapping out a galaxy. Each star represents a possible configuration. Some stars improve your material model, others don't. The acquisition function helps you find the brightest stars, those most likely to lead to breakthroughs. After identifying a promising data point, the researchers updated their model and ran it through the FEM again. This cycle repeated over and over until they had integrated 100 new data points into their model, each one improving the material's predicted properties. So, what did all of this lead to? The The study focused on a particular type of nanoarchitectured carbon material, pyrolyzed carbon nanolattices. Pyrolysis involves heating materials to very high temperatures in an oxygen-free environment, effectively transforming polymers into carbon while maintaining a net-like structure at the nanoscale. This structure gives the material its remarkable strength and lightness. Thanks to the fusion of FEM and Bayesian optimization, the team significantly improved the mechanical properties of these nanolattices. They boosted the material's stiffness by an impressive 68% and its strength by a whopping 118%. But theory alone isn't enough. These findings had to be validated in the real world. To do this, the researchers employed a technique known as two-photon polymerization. A precisely focused laser beam hardens a light-sensitive polymer at specific points, forming a three-dimensional nanolattice. They then applied pyrolysis, converting the polymer into a carbon-based structure. The final product? A carbon nanolattice with a compressive strength between 180 and 360 megapascals, comparable to carbon steel, and a density between 125 and 255 kilograms per cubic meter. You might pause here and think, isn't 125 kilograms per cubic meter a bit heavy for something being compared to styrofoam? It's important to note that this figure aligns more with specialized types of styrofoam used in protective gear like helmets, which typically range from 90 to 100 kilograms per cubic meter. In contrast, construction-grade styrofoam is much lighter, around 15 kilograms per cubic meter. The comparison might be a bit playful, but it's powerful. Carbon steel has a density of about 8,000 kilograms per cubic meter, so achieving the same strength at 64 times less density is genuinely astonishing. But as with all cutting-edge innovations, there are challenges. Before we dive into those, if you're enjoying this breakdown, consider subscribing and hitting that bell icon so you never miss an update. Back to the hurdles. While FEM can model many physical scenarios, it struggles with size-dependent effects, especially at the nanoscale. This means some material behaviors are still difficult to predict accurately, but the most significant challenge lies in scalability. Producing these nanostructures is time-intensive and not yet suited for mass production. In particular, the pyrolysis step needs further refinement to make it more efficient and viable for industrial applications. Another issue is homogeneity. Ensuring consistent material quality across large volumes is still tricky. And yes, the comparison to helmet-grade styrofoam might be stretching things a bit, but it's effective in helping people visualize just how light this material is. All in all, though, this development is exciting. It shows how merging well-established scientific techniques can open up entirely new possibilities. This approach is still relatively young, which means there's room for significant improvement and innovation, especially as AI and machine learning continue to evolve. We might uncover entirely new properties and applications that we haven't even imagined yet. So what does this mean for us? Potentially, it could lead to a new generation of ultralight, ultra-strong components for planes, cars, and even spacecraft. Lighter vehicles mean lower energy consumption, lower emissions, and a more sustainable future. What do you think? Can you imagine how game-changing it would be if airplanes and cars could be made drastically lighter without compromising on safety or durability? The potential here is truly enormous. Let me know your thoughts in the comments. Until next time.